All right, we're going to talk a little bit more about cardinality today and then move on to something completely different. Actually, this cardinality stuff, in my opinion, is very interesting, but it's not really what we're going to focus on for the rest of the course. This is what we were talking about at the very end last time. This is Cantor's famous diagonal argument for showing that the real numbers is uncountable. So remember how it works. If you had some alleged listing of all the real numbers, one after another, it turns out you can always create another real number which is not in the list anywhere. So the way that this number is created is specifically this number is created to be different in each decimal position from all of the numbers in the list. And I did that by just taking each decimal digit and increasing it by 1. And if there was a 9 in there, I would change it to a 0. All right. So what this argument demonstrates is that no listing can include all real numbers, right? Even an infinite list, just the fact that it's a list where it goes one thing after another, means that it is not possible that it includes every real number. It can include, include infinitely many things, but you can always, by this argument, you can always create a real number which is not part of the list anywhere. All right? No listing can include all real numbers, so that the fancy word for that is R is uncountable. It's infinite, but more so than, say, the natural numbers, which all exist in an infinitely long list. R is infinite, but you can't even write it as a list. All right. I wanted to say, so this means, if you will allow me to use this like number sign to mean the cardinality, the cardinality of the real numbers is greater than the cardinality of the natural numbers, right? The natural numbers cardinality, this is countable, and the cardinality of R is more than that. Actually, Cantor had names for these different cardinalities, and he used, this is one of the only areas in mathematics where this is mainstream, but Cantor used the Hebrew alphabet. Usually we stick with the Latin and the Greek alphabet, but Cantor actually used the Hebrew. And my Hebrew, I'm no good at writing Hebrew alphabet letters, but he used Aleph, which is the first letter of the Hebrew alphabet, which looks something like that. It's kind of, I don't really know how to write Hebrew letters, but this, the cardinality of n, anyone out there better writing Hebrew letters than me? Probably. The cardinality of n, he called Aleph 0 or Aleph naught, and this one he called Aleph 1. It's bigger. It's Aleph 1, all right? But soon after, people started doing crazy things with the Alephs, and people right away tried to answer questions about, well, are there other kinds of infinite sets, like other cardinalities greater than the cardinality of R? The answer is yes, there are. There is such a thing as an Aleph 2 and an Aleph 3. The standard way to get this is by taking the power set. Remember, the power set of a given set is the set of all subsets. And for a finite set, the power set is much bigger. If you have a set of, for finite sets, if say the size of A is n, if A is a finite set with n elements, then the size of the power set of A. Anyone remember this? The power set is the set of all subsets. There's a formula for that. Like if you had three elements in a set, the set of all subsets of that, there's 8 different subsets you can make out of 3 elements. Remember this is 2 to the n. It's always much bigger. The power set of a finite set is much bigger than the original set, exponentially bigger. All right. And Cantor actually showed this same basic diagonalization argument in general can show that for any infinite set, S is the cardinality of S is smaller than the cardinality of the power set of S. When you take the power set it turns out, I don't want to get into the details of this, but it turns out you always get a larger set than the previous one. Even if they're infinite, you get a infinitely a larger set of different cardinality, all right, between an original set and its power set. And so we can make many large cardinalities, because if you start with, you can start with n, the size of n. Well, how about we just start with the size of r? This is less than the size of the power set of r. So if you want an infinite set which is even bigger than r, you can take the set of the power set of r. That is to say, the set of all sets of real numbers. That is a cardinality even bigger than the cardinality of r. And if you want one even bigger than that, we can take the power set again. So this is less than the power set of r. This would be the set of all possible sets of real numbers. It gets increasingly silly, but these are real things that you can talk about, and they are even bigger than one another, I'll just say, etc. This is how you get like Alephs2, Alephs3, and so on. And if you want to be really insane, you can even get ones that are bigger than any of these. So this is like Alephs2 is like this one. Alephs3 is like this one. You can even, I'll just say, there's even Aleph. You ready for this? What's the biggest you could possibly imagine? You might say, can you go to like the Aleph infinity? You wouldn't really say Aleph infinity because you would be more specific. You can do this though. There is such a thing as that. Aleph not, right? Isn't that even better than Aleph infinity? It's like this, but instead of that number down there, it can be another infinite cardinality. So, and of course you can go crazy with this. This can go on forever, right? You can do Aleph eventually. So you get the idea. There's many super large sizes of infinity that you can get by doing this. All right. Any thoughts about that? This I present just for your information. We're not really going to talk about these things, but if you're into that, there are people who talk about this. It's like, in my opinion, super deep stuff. Okay, one last thing that I want to talk about, so more or less for your information, although I think it's very interesting. A big question that arose after all of this business. So we know Cantor demonstrated that the size of n is less than the size of r. And a question that was immediately raised by Cantor himself, Cantor asked, is there a set in between? Is there some other cardinality which is bigger than n but lesser than r? And this Cantor decided this was a really hard question that he couldn't answer, but he sort of presented this to other people, and this eventually had a name associated to it. This is called the continuum hypothesis. And this was proposed by Cantor, although, like I said, Cantor was not able to prove it, in 1878. The continuum hypothesis says there is no set S with the natural numbers less than the size of S less than the size of R. This is called the continuum hypothesis. And I'm going to abbreviate this as CH, if you don't mind. The continuum hypothesis. Cantor proposed this question. He was unable to prove it, but Cantor believed that there was no set in between. That's called the continuum hypothesis. And this very quickly became a big deal. So this was 1878 that he first published this, but I would just say by 1900, this was a big deal. Lots of people were working on this. And in the year 1900, there was a major conference, a worldwide conference of mathematicians, where this mathematician named Hilbert, David Hilbert, who was kind of a top dog at the time, and he took it upon himself to create a list of problems that he believed would be the most important unsolved problems of the new century. This was in the year 1900. And Hilbert's list of problems, there were like about 20 problems on the list. They all became famous, and they were like, if you look at the history of 20th century mathematics, much of it was based on solving the 20 Hilbert problems. There was a little bit more than 20. And, people who solved these numbered problems became instantly famous as mathematicians, and there were careers made and broken on the Hilbert problems. And most of them have been solved by now, but some have not. And actually, this was so influential for the 20th century that in around the year 2000, somebody created a list of the new problems for the new century, which are these are called the Millennium Problems, and there were 7 of them. Maybe you heard of some of them. One of them has been solved, and the others are still unsolved. And they all have, the Millennium Problems all have $1 million prizes associated to them. I told somebody this, and somebody asked me once, so if you solve them, you get $1 million. Yeah. Do I have to solve all of them to get the $1 million? No. That was a cute question. This is like saying, to get a gold medal at the Olympics, do I have to win every event? No, like nobody could ever win every event. Nobody's going to solve all of the Millennium Problems. Anyway, this was the continuum hypothesis was listed number 1 on Hilbert's list of important problems for the 20th century. And let me tell you, the continuum hypothesis by now is more or less figured out, but it was figured out in a very strange way. That's why I'm telling you about this, because this is weird. I will tell you, in 1940, a famous guy named Gödel was working on this. Gödel was very much involved with the kind of mathematics that Alan Turing was doing about the nature of computation and algorithmics. And Gödel couldn't prove it. Everyone was trying to prove it or disprove it. Prove it means you demonstrate there can be no set in the middle. Disproof would be you just come up with a set which is in the middle. Anyway, Gödel couldn't prove it, but this is the weird part. Gödel showed that the continuum hypothesis will never lead to a contradiction in set theory. So this is very strange, but basically what happened is Gödel did not prove that it's true, but he basically proved that you can't prove this by contradiction. He said that even if you assume that it's true, that cannot derive a contradiction. So really this means you cannot prove the opposite of the continuum hypothesis by contradiction. All right? Anyway, if it's true, it will never lead to a contradiction in set theory. That's what Gödel showed, which is a little strange. You might wonder, doesn't that just mean it is true? And I would say, I don't know. I mean, it's kind of like my mommy thinks I'm the best boy ever. That does not lead to a contradiction in set theory. Does that mean that it's true? I don't know. Like, it's a weird thing. But anyway, this is what Gödel showed in 1940. And then, here's the extra weird part. In 1963, a guy named Paul Cohen showed that continuum hypothesis will not lead to a contradiction if it is false. So Gödel showed that if it's true, it leads to no contradiction. And Cohen showed that if it's false, it leads to no contradiction. All right? What this means basically is it might as well be true or false, and you can never prove it either way. That's basically what that means about the continuum hypothesis. If you think it's true, go for it. It doesn't matter. It doesn't affect the rest of set theory. It will not lead to any contradictions. And if you think it's false, the same is true. It can be true or false, and either way is okay. Which essentially means it can't be proven to be true or false. All right, so we now know the moral of the story is, in ordinary set theory, which is what the continuum hypothesis is about, ordinary set theory. The continuum hypothesis can't be proven true or false. And there is now a word for this. When Cantor came up with this idea, there was not a word for this, but this is nowadays, this kind of a thing is called, it is undecidable. It is an undecidable proposition. That is, it's a real mathematical theorem. It's not something like, I'm the best little boy ever. It's like, it actually means something, and it is a real mathematical statement, but it cannot be proven to be true or false. It is undecidable. And so now, actually, in the way, in ordinary mathematics of today, this is always kept in the back of our minds when we're trying, when I have a theorem that I'm trying to prove, say in my own research. I assume that it's either going to be true or false, but in the back of my mind, I do recognize there's a possibility that it is undecidable. This almost never happens with a typical problem that you're likely to encounter. You know, your homework questions in a calculus class are never undecidable, but there are undecidable theorems in mathematics. And so nowadays, like for instance, the Millennium problems, you get $1 million for proving this theorem is either true or false. And there's like as part of the contest rules, proving that it's undecidable, that counts also. So you get the $1 million. That's also a resolution. Not all mathematical theorems are provable. That's kind of what's interesting about this, in my opinion. Not all mathematical theorems are provably true or false. Some are just undecidable. There's a famous 20th century mathematician named Paul Erdős. He was a number theorist, but he had a lot of sort of cute little quotations, kind of like Einstein. And he had wild hair also. But one of his cute sayings that he had was, when I die and meet God in heaven, the first thing I'm going to ask him is the continuum hypothesis true? Because this is a question which is simply unanswerable by ordinary mathematics. And apparently God knows the answer. I don't know. To me, I feel like God would probably say it's undecidable. When we say it's undecidable, that's not like that doesn't mean like we're stupid. That's why we can't decide it because we're too dumb. I think whatever situation we're in, maybe God is in the same situation. It's not because we're too stupid to solve it. It's because there just isn't a proof of continuum hypothesis one way or the other. Question?
Yeah, I was going to ask, like, I don't know, doesn't that kind of prove that it's undecidable?
Yeah, right. That's why, I mean, this business about if it's true, there's no contradiction, and if it's false, there's no contradiction. That means you can't decide it. Yeah.
So I was just wondering, because you mentioned like proving that it's undecidable as part of it.
Oh yeah. Yeah, so you.
Is it already proven to be undecidable?
Yes, it has been proved that it's undecidable. You can make it sound silly by saying, "Oh, you mean you can prove that there's no proof?" Yes, that's what it means. You can prove that there is no proof for the continuum hypothesis. Yeah.
So, does that mean that you can't use the continuum hypothesis in like other things?
That's like a cultural question, I guess. But the short answer is no. People use the continuum hypothesis all the time. But there's a big, there's sort of a body of work which is based on if we assume the continuum hypothesis, then what other theorems can we prove? So there are lots of people who prove theorems based on the continuum hypothesis, but they'll always be very specific about, I'm using the continuum hypothesis, like listed as a red flag, because it's not something it's not like an ordinary mathematical theorem. But then there are just as many people doing work which is based on the opposite of the continuum hypothesis, because that is also a valid thing. So people do both. It's sort of a philosophical question then, like which one is actually true, the continuum hypothesis or the opposite? And I suppose Paul Erdős thinks that there's an answer to that question. I think I don't know what you can ask your other math professors what they think. Do you think the continuum hypothesis really is true or really is false? My interpretation of this undecidable thing, I would say it doesn't really make sense to ask, is it really true? Because it's an abstract concept. I mean, I can say there's no proof of it. Whether you think if you want to interpret that as meaning it's not really true, that's up to you. How you want to think about it. Yes?
So, you said before the power set of R is greater than N.
Yeah. Greater than R, yeah.
So the power set of N is greater than N.
So actually the power set of N, this is a point which I'm not quite sure of the details. So this may be slightly wrong, but I believe that the power set of N is there's a bijection to R. The power set of N is actually the same as this, but I think maybe that uses the continuum hypothesis. So the exact relationship between the power set of N versus R, I think, is related to the continuum hypothesis. So yeah, that's something I'm not quite sure about. That is definitely known, though. Some people who are not me know all about this stuff. All right, let's move on then. So that's all that I want to say about cardinalities and so on. Basically, everything that we talk about in this class will be about either N's or R's. So it'll be either uncountable, or it'll be countable, which is to say the size of N, or it'll be the size of R. And that stuff is not really going to come up much otherwise. But the reason we talked about it all is because it is a consequence of the completeness axiom. The axiom of completeness in the nested intervals property is what allows you to deduce that extra number over there actually exists. And this is the end of chapter 1 in our textbook. So we are going to move on to chapter 1 was just kind of introduction and the completeness axiom. Chapter 2 is all about sequences and series, which is going to be a big deal for us. Sequences and series. This is something that you talked about in your calculus class a bit, I think, but we're going to try to get real specific about the details of it in a way which was probably skipped over in your calculus class. Let's just talk terminology here. Those two words mean different things. So a sequence is just an infinite list of numbers. Countable, of course, because it's a list. A1, A2, A3, etc. All right. And usually, when we write in this class, when we write a sequence, we're going to put it in those kinds of parentheses, the roundy parentheses. And this, if I wanted to write it, give it a name or something, I would call it that. AN in parentheses. So if you ever see AN in parentheses, this is meant to represent an entire sequence, A1 through A1, A2, etc., up to infinitely many things. All right, that's a sequence. A series is when you add them up. Oh, let me say before I say this, I will say this may or may not have a limit. And this is a major thing that we're going to talk about when it comes to sequences, whether the sequence has a limit or not. All right, and then a series is an infinite sum. This is when you add it all up. So you start with a sequence, and then you add all the terms together. And this, of course, we would write this way usually. We use the infinity sign. Why not Aleph 0? Because everybody knows what I mean when I put the infinity sign there. All right. This is, of course, the infinity, which means that the size of n, but people don't usually care about writing that down. All right, and this one may or may not, the word for series is, we say, may or may not converge. All right, that's a series, is when you add together an infinite amount of stuff. All right. We're going to talk first about sequences, and we'll talk about series a little bit eventually, but let's talk about sequences first. For example, something like 1, 1/2, 1/3, 1/4, right? This, another way of writing it would be 1 over n in parentheses like that, right? That's how we're going to write that sequence. This is the sequence where each term is 1 over n. When I use n, remember you assume n is a natural number, which is to say starting with 1 in this class at least. All right. How about 1, 2, 3, 4, etc. This, if you were writing it in that style, would just look like n, right? It is the series, the sequence of just n. Or you can do more complicated things. Something like an is the sequence, 3 plus root n over 4n squared, something like that. This is typical sequence that we might want to talk about. All right, this is just a notation for how we would write a sequence. Our first major kind of important thing to talk about for sequences is convergence. And this is immediately getting to the big deal that I said, the big sort of detail which I said was typically left out of a calculus class is, what do you really mean when you say that something converges to something else? The limit of something is something. That's what I want to talk about. So let's talk about convergence. For example, of these sequences, the first one there actually converges. This 1, 1/2, 1/3, etc. This sequence, this one converges to, what I mean by that is, as you go down the list, eventually these numbers get closer and closer to a certain other number. What is it? You say? 0, yeah. This sequence converges to 0. It's because if you were to, say, draw the numbers in the sequence, you have 1 first, and then a half, and then a third, and then a fourth, a fifth, etc. These eventually get really, really close to 0, all right? That sequence converges to 0. I want to try and say, though, what exactly do we mean by that? Well, sorry, one more bit of notation here. We'll write, this sequence, of course, is just 1 over n. Lim 1 over n equals 0. Notice that in this class, we are never really going to write, in a calculus class, you would write this all the time, but I'm not going to write anything under this lim. Because I am always, when I'm talking about a sequence, there's only one thing that goes anywhere, and it always goes to infinity. So every lim, this, you can imagine, this lim is like lim n goes to infinity. But actually, if we're talking about sequences, it's always going to be called n, and it's always going to go to infinity, because a sequence doesn't go anywhere else, the n at least. We're talking about what happens when you go all the way down the list. That means what happens when the n is going to infinity. So we are always just going to write lim with no other funny business. It doesn't even make sense to write, well, what about lim n goes to 3 here? Now in calculus that would make sense, but in terms of this sequence, there's no sense in discussing the limit as n goes to 3. Because the only place the n goes is out to infinity. All right? Anyway, lim is what we're going to write. What we need is a real definition of this. All right? What does it really mean? As I've said in the past, this business about as n gets really, really big, something or other gets really, really close to 0. This is not real technical language. This is kind of like the when a mommy and a daddy love each other very much kind of language. I want to say very specifically what this really means. What does it really, really mean? 1 over n, let me just say, this is not what it really, really means, but it means 1 over n gets really, really close to 0, right? When n is really big. Maybe I'll write that also. All right, how are we going to turn that into a real mathematical statement? Well, based on the kinds of stuff we've been talking about already, this is not the same as anything we've been talking about before, but it's you can express this in language using epsilons and saying things like for all epsilon greater than 0. So this really, really close to 0 business, the way I'm going to say that is basically something like this. 1 over n is less than epsilon for all epsilon greater than 0. All right? That's kind of what you mean by this, is that I'm not actually saying that 1 over n equals 0, because 1 over n never does equal 0 in this sequence. You can't actually make it equal 0. But if the n is big enough, you can really make 1 over n smaller than any other number, all right? By taking the n to be big enough. So you basically want to say this. I'm writing this in red because this is not like my final answer, but this when n is big enough. All right? I'm trying to get there in little baby steps, but this is basically what the true definition is going to look like. It's going to say my sequence, 1 over n, ends up being less than epsilon, no matter what epsilon is, provided that the n is big enough. So actually, to be a little more technically correct about this, really what it should say is, for all epsilon greater than 0, this part we still need to make some sense of, but when n is big enough, 1 over n is less than epsilon, all right? One way of talking or thinking about this is, like, how small do you want 1 over n to be? What I'm saying is 1 over n gets really, really close to 0. It gets really, really small. Well, how small? The answer is, okay, no matter how small you want it to be, you want it to be less than epsilon, all right, no matter how small that is, then it is true that n is eventually going to be smaller than that, no matter how small you say. What does this when n is big enough mean? One way to formalize this is to say, no matter how small you want it, you got an idea?
Can we just say there exists?
Yeah, right, that's what I'm going to say. No matter how small you want it, there is some big enough n which makes these things always that small. So this is going to be a there exists. So my final way of writing this is like this. For all epsilon greater than 0, there exists some, I'm going to call this a big N, a natural number. This you think of as like some kind of threshold. No matter how small the epsilon is, there's some point eventually down the list somewhere, the sequence gets to be smaller than epsilon. So there exists some n in the natural numbers such that, this is a little technicality, if n is bigger than the big N, then 1 over n is less than epsilon. So basically this says, beyond this big threshold, all the rest of the terms are smaller than the epsilon. Beyond some particular threshold point, all of the rest of them, that is anything which is beyond that threshold, they're always going to be smaller than epsilon. Is that not what you wanted me to say? Do you want me to put the big N right there? I think that. Yeah. So this is more complicated than another thing that you might have in mind. Don't write this down because this is not correct. But you could also think of, what if I just to make it simpler, there exists n in the natural numbers such that 1 over n is less than epsilon, right? This means no matter how small you want it to get, there is eventually some value that is small enough, that is that small. This is okay actually for this simple sequence, 1 over n, but generally in order for something to converge, it means that all of the values get really close to the point where they're converging. Not just that there is one value which is really close to it, which is what this means. So this means there is some one individual value that's really close. This means all the values beyond the threshold are all really close to the limit, is what we call it, right? Which is why this one is the more correct definition, right? So this is the idea. Let me just write this out as a complete definition, because I know that was a bit disjointed here. So here's my definition. Yes. So I'll say let an be a sequence. We say that an converges to some limit a. You have to say what the limit is. In this case, I'm saying the sequence an converges to some particular number a when, and here I'm going to write all of that stuff. For all epsilon greater than 0, there exists n, a natural number, such that n greater than n, little n greater than big N implies, or did I write if? I'll write if then. You can write with the implication sign. I'll write it with the implication sign. If the little n is bigger than big N, then, now before I wrote like 1 over n less than epsilon, although that was specific to the sequence 1 over n. Generally what it is this. Absolute value an minus a is less than epsilon. This, of course, is the distance from an to a. So what I'm saying is it converges to a. What that means is that eventually all the values are within epsilon of a. The distance from each term in the sequence to the a gets smaller than anything. This is less than epsilon for all epsilons. All right? This is a very complicated definition of what seems on the surface to be a simple concept of something getting closer to something. Yeah, question?
So like for this definition, that like big one, that's like our does that change depending on what epsilon you pick, or is that like a set?
Yeah, no, the big N will depend on the epsilon, just like over here. Like in this example, if you say the sequence is converging to 0, means it gets as close as you would like. If I say, well, how far do I have to wait until it gets within 0.1? That's a particular n. How far do I have to wait till it gets within 0.0001? That's a different n, because you have to wait longer until it gets that close. Yeah, so this n will depend on the epsilon. I will say, usually. I mean, in some very simple cases, it doesn't depend on epsilon, but usually. What I wrote there. All right. This was the great achievement of Weierstrass and those other people who came up with this same basic idea. This is the definition of convergence, which had escaped people for many centuries, either because they couldn't figure it out or because they didn't care, sort of a mixture of the two. This is the definition of convergence. Let me just say one last thing as part of this definition. In this case, we write lim an equals a. All right, so when I write that, the limit of an equals a, what I mean is the sequence an converges to a, and what that means is all of that business. Right? This stuff here, I will say, you should memorize this. It's very technical, I know. But I don't know if you're gonna ever have to sit down and memorize, but we're gonna be doing this over and over again during the semester. So definitely memorize that. All right. We got 12 minutes. Let's see if we can do an example to show that something converges to something is actually quite involved because you have to demonstrate this thing. Let's see if we can do it. Simple example, let's just try and do that one. Let's show that lim of 1 over n is 0. This is like the easiest example you're ever going to do. All right. What we need to show, I'll just refresh my memory. I want to show that for all epsilon greater than 0, there exists n, a natural number, such that n greater than big N implies absolute value an minus a less than epsilon. Right? That's the definition that we're going to be using. And really, what you have to do is a little sort of miniature proof every time you show that something converges to something else. You have to write a little proof. The proofs are kind of formulaic in that the logical structure of the proof is usually going to be the same, so you won't feel like you're writing a proof, say, in set theory. But you do have to write yourself a cute little proof here. So I'm going to just write like a proof. And I'm going to tell you, the proof always has 3 basic steps to it. And I will try to delineate those steps here. Ordinarily, if you're doing this on the homework or something, I wouldn't expect you to like number your steps, but just for the sake of discussion, I'm gonna put a little number. 1. You always begin this proof by saying let epsilon greater than 0 be given. And then what do I have to do? I have to find some big N, because that's what I have to show is for every epsilon, this business is true. So I need to find some big N. We'll find N, a natural number, such that N greater than N implies. Can we fill in a little bit of the details here? AN and A, actually they have specific, I'm doing a specific example here. So what is AN in my example? I think it's 1 over N, that's the sequence I'm talking about. So I'm just going to plug that in. Minus A, what is A? It is 0. Yeah, A is the limit of the sequence. So I guess I'll just write this in like that, right? This is what we have to do. Let epsilon greater than 0 be given. We will find some N such that N greater than the big N implies 1 over N minus 0 in absolute values less than epsilon. All right? That was step 1. This is totally formulaic. If you were doing this on a test or something, you have had no thoughts yet, right? Because this is just copying what you have to do. All right. Step 2. This is where all the business happens. And the business, as we are going to write it, is usually sort of written on the side, but step 2 consists of choosing this N. And I'm just going to say it. Choose the big N to be greater than 1 over epsilon. Where did I get that? That's another story. And this is what is hard about writing these proofs is figuring that part out. All right, but I'm gonna postpone that discussion. So choose N to be greater than 1 over epsilon. I'm gonna sort of circle that and say this is the hard part. And then step 3 is now you just verify that that N actually satisfies this property here. So how do we verify that? We let little n be greater than the big N. And we have, and here I am going to actually demonstrate what the ultimate conclusion is this, right? And this thing, all right? So in order to demonstrate this inequality, I'm going to start with the thing on the left side and do a bunch of simplifying. So I'm going to start with this. In black. 1 over n minus 0. I'm going to do a bunch of maybe equal signs, maybe less than signs, eventually saying less than epsilon. That's where I'm going with this. And if I'm able to do that, that's the end of the proof, right? Because that's what I needed. That's what we needed to demonstrate. 1 over n minus 0 is less than epsilon. All right? Can we do it? I'm going to erase this. That's where we're going for, though. I want to put a bunch of either equal signs or less than signs, simplifying this, hopefully, and eventually ending up with epsilon over here, using only equals or less thans. Don't use greater thans, because then it won't work. Any ideas? How can we simplify this? Well, first of all, I know how to do 1 over n minus 0 is 1 over n. So this is equal to absolute value 1 over n. You will see when doing these proofs, one of your biggest enemy will be the absolute value signs. Handling the absolute values is usually a pain. Now, maybe I already mentioned my go-to technique for handling absolute values as a young man was I just ignore the absolute values. Now, I'm not a child anymore, so I should think, is that actually legal to do in this case? Yeah? Yeah, because n is a natural number, that is legal. Now, if this had said 1 over 1 minus n, you've got serious problems. But n is a natural number, that is, it's a positive number, and so you can do that. All right? Okay, what else? Here's a little trick. I want to, I have to somehow use this. So I need to change this scenario into something about the big N. Would you agree that this is true? This is because the little n is bigger than the big N. And since it's in the denominator here, It means 1 over the little n is lesser than 1 over the big N. What I did to go from here to here is I made the denominator smaller, which means the fraction becomes bigger. This, I don't know about you, but I find this, even though I'm not a young man anymore, I find this persistently confusing. I always have to think hard to myself. Did I just make that thing bigger or smaller? Unfortunately, that is going to be involved in our proofs all the time in this class. One strategy is you just write it this way because you know how it has to work out, but you will often fool yourself into thinking you did it right. But anyway, this is correct, all right? I made the denominator smaller, which means the fraction gets bigger. Okay, anyone want to guess? Remember, I intend to end with just epsilon over here. Anybody? Yeah.
In step 2, we could do epsilon.
Yeah, for the same reason, the big N is greater than 1 over epsilon, so this is less than 1 over 1 over epsilon. I replace the N with 1 over epsilon. And any masters of fractions out there, what is 1 over epsilon? It is epsilon. So actually this equals epsilon. And we're done. I will say as desired. All right, this is how these proofs always go. You do the first step, which is basically just setting the scene for the whole thing, right? There's no work there. The second step is where the work happens. You have to sort of produce this thing out of nowhere. And that's what we need to talk about in more detail. But then the third step is really just kind of verifying that the second part was correct. You are demonstrating that actually, when I use this big N, you actually do get this thing being less than epsilon, which is what you wanted all along, all right? I actually have names for these 3 steps. This is inspired, I don't know if you are familiar with, this is a Christopher Nolan film. It's kind of an old movie called The Prestige. Anybody seen this one? It's got Christian Bale and Hugh Jackman as 2 battling magicians. They're like stage magicians. It's really good. I like Christopher Nolan. The Prestige. Check it out. You should watch it. It's good. Featuring David Bowie in a cameo. Good stuff. The Prestige is about these 2 magicians, and it has the guy who played Batman's butler in those movies. What's that guy's name? Yeah, Michael Caine as Christian Bale's buddy. No, maybe he's Hugh Jackman's buddy. He's like the old buddy, just like he is in the Batman movies. And the Prestige. So in the Prestige, this is the famous line by Michael Caine, which is where the title of the movie comes from. He says, every good magic trick has 3 parts, and they happen to be these 3 parts. The first part is called the pledge. Part 1, the pledge. The magician shows you an ordinary object. That's the first part of the magic trick. So this is just shows the ordinary object. The magician shows you an ordinary object. So in step 1, all we're doing is just writing down what the scenario is that we're dealing with. Step 2 is where the magic happens. This is called the turn. And this is the magician makes the ordinary object do something extraordinary. So this is like, in step 1, maybe the magician shows you their empty hat, and then step 2, they pull the rabbit out of the hat. Makes the ordinary object do something extraordinary. And Michael Caine says, now a lesser magician will stop there. That's the end of the magic trick to some people. But no, the true great magician does the third step, the prestige. And that's what the whole movie is also like, cinematically fits this same general pattern. It's deep, yo. It's called the prestige. The prestige is the magician reproduces the ordinary object again, just as it was at the beginning. So this is like putting the rabbit back in the hat and then showing you again the empty hat. This is the true mark of the true master of the craft. So this shows the object again. As it was. All right, and that's really what sort of step 3 is. So I call this step 3 is like the prestige. You are just using the step 2 is where the real work goes into it, but in step 3 you are just verifying that your choice in step 2 was correct. All right, yes?
Would you make like a final statement that means that n is greater than whatever else?
No, I would just leave it at this. This is the end of the proof as far as I'm concerned. Because you're not actually trying to prove that n is greater than epsilon, than 1 over epsilon. What you're trying to prove is this, that this is less than epsilon, and that's what you just did. So we're going to do lots of examples like this next time. See you all then. Let me know if you have homework questions. And watch that movie. It's good.